So we need, whenever when you submit these K queries, we need to have this plausible argument across all the queries. So the queries should be equally plausible. Okay, so this is a setup. What happens in the plausibly deniable search. The user original query is Q3, and the user is generating this set of K queries. The set of K queries are submitted to the search engine, and we call this set as a PD query set, plausibly deniable search query set. Okay, once the search engine has the K queries, it could say, okay, I know you searched for Q2. Okay, that's a claim by the search engine. But you can say, no, I could have searched for Q1. Why? Because if I use the plausibly deniable search, the Q1 also gives me the same set, Q1 to QK, which gives you the deniability argument. You can deny issuing any of the queries there in the set. And also, we have the property that all the queries are plausible user queries, the plausibility argument. Okay, so now we look at what are the characteristics of the K queries in that PDS system. So the first criteria is that we want each query in the PD query set to be a standard query. Okay, if you allow the user to create any possible queries, the spelling mistakes or the way you construct the queries will automatically lead to a situation in which one query will stand out from all the other queries. So you want to have each query to be a standard query. So that is the standardization we do before creating the set. The second is that deniability argument. For any query in the set of K queries, we should be able to get the reversibility. Any one of the K queries should be able to generate the same set, which will be issued to the search engine. Okay. Third criteria is the plausibility and diverse topics. So if one of my queries is related to basketball, and the rest of the queries are also related to basketball, then there is no reason you have to use this technique, right? Because all the queries are on the same topic. So you need to have the diverse topic criteria. So all the K queries should be on different topics. Okay. So this shows the steps in this PDS system. The first step, you create a set of standard queries from a collection of documents. And the second step, you create this PD query sets based on the criteria we have defined. The query should be deniable, reversible property, and also the plausible property. The third step, what you do when a user, ordinary user, wants to issue a query, what do you do? So that's the final step we'll talk about later. Okay, the first step, creating canonical queries. Okay, so what are these canonical queries? Okay, these are the standard queries issued in place of the actual user queries. For example, basketball, NBA, or USA basketball could be replaced by a common query, more general query basketball. And also queries such as Purdue computer science and Purdue statistics could be replaced by a Purdue computer science statistics. So the canonical queries serve two purposes. One is that they do not reveal the actual query. They provide one level of anonymization. And second is that they replace the original query with a more related, semantically related query. For example, basketball NBA I should replace with basketball, not baseball, right? I want a similar query, and that's what the canonical query should achieve. Because you need to provide the users with the results they want, right? Okay. Now the question is, how do you create all possible canonical queries from a document collection? Right? Because what we're saying here is that we pre-compute all these possible queries, and how do you do it? Okay. Let's say we have a document collection, M documents, and from the document collection we create this list of terms, N terms, and with that we can also create this term document matrix where each entry, A, J is the frequency of term I in document J. Okay, once we have the list of terms, we can create this power set of this term set to create all the possible queries, right? That's a kind of obvious way, but which is not going to work because for large n, it is impossible to create all possible queries. Okay, the way we create this canonical query is by computing set of seed queries. What are these seed queries? Basically, they are single terms or term pairs that occur in the document collection more than delta times. We can delta could be 500 or 1000 depending on your construction criteria. So what we are saying is that okay, I know these single terms and these pair of terms occur more than 500 times in the document collection. That means they are significant to significant terms in the collection itself, right? Because they occur more frequently. So this to find the frequent terms, we can use tools such as frequent pattern mining, which are very efficient on the term document metrics. For example, frequency of IBM could be in the document collection could be occurring more than delta times, and also IBM DB2, because DB2 is a product from IBM and jointly occur more than delta times. And also, single terms and the the term pairs are not sufficient to represent all possible user queries. So what we do, once we have the single terms and term pairs, we use a latent semantic indexing to kind of combine together the semantically similar seed queries to form the canonical queries. Okay, so if you don't know about latent semantic indexing, I'll just give a brief introduction here and then move back to the canonical queries construction. It's claimed that the latent semantic indexing is used by search engines such as Google these days. So it's an important IR technique. Okay, basically it's commonly used in IR to create concepts, concepts as in topics from a document collection, so that terms and documents are related to set of topics or concepts. So the way it is done is used by using singular value decomposition. Basically, you decompose the term document matrix to 3 different matrices, so that the product of these gives you A. So the matrix U here gives you the relation between terms to concepts or terms to topics, and also the matrix V gives you the relation between concepts to documents. And instead of keeping, if you look at the size of U, it's n across n, but if you just keep R columns there, it gives you a representation, basically a concept space, which we can represent the terms in a concept space with using only R dimensions instead of m dimensions. So it's a dimensionality reduction. Also, it gives you a way to represent the terms in a topic space. So once you have the representation, you can compare topics of terms in this semantic space. Okay. Now, so we have a way of converting queries to points in the semantic space using this equation. And also note that the number of dimensions here is R, which is very less compared to m, the number of documents. Okay, let's go back to the canonical query construction. So we have the set of seed queries, and you want to create this canonical queries. So for each seed query, you find the other 2 closest seed queries in the semantic space. Basically, what I'm saying is that take a seed query, and what are the other 2 top 2 seed queries which are very similar in topic to this particular seed query. So you can use this based on the Euclidean distance between the seed queries to merge 3 seed queries together to form a canonical query. The example here, IBM DB2, it's a term pair which occurs, let's say, more than 500 times in the document collection, and also database which occurs more than 500 times. And in the semantic space, if these 2 are together, that means they are topically related, So we can combine them to create a new query, a canonical